To get to the heart of the global warming story, the very heart of it, it turns out that the scientific explanation hangs on the behavior of one very particular atom.
That atom being carbon.
The more you know about carbon, says Professor Dan Nocera, who teaches chemistry at MIT, the more you'll know about global warming. Carbon is the key. First, because it's everywhere. The lead in a lead pencil, really carbon. Diamonds, carbon. Professor Nocera.
Yep.
Mostly he's water, but if I squeeze them like a sponge, you got all the water out of Dan. Well, his dry weight, the non-water part, is what part carbon?
It's a big percentage. I don't know that number.
Well, we looked it up, and all dry Dan's about 2/3 carbon.
Yep. Carbon is the central element of life.
So much so that everything that is alive, and I mean everything, a housefly, a rooster, a tiger, from the smallest yeast to the biggest thing you could imagine. Here, this is a singing whale. Inside every cell of every creature bar none, if you look, you will find carbon. And why? Because, says science writer Natalie Angier, carbon is the duct tape of life. It's what holds living things together. That's carbon's job.
Carbon next to carbon next to carbon, all holding hands.
In a limp sort of way or in a firm grip sort of way?
In a firm grip sort of way.
Grab your partner, don't let go. Grab 'em hard and do-si-do.
If you think of carbon atoms at, say, a square dance, not that you would, but why not? You are looking at a very social atom which likes to grab hold of a partner, and not just one partner, but sometimes four, simultaneously.
Okay, carbons, grab a friend. Promenade and grab again. Keep on grabbing, form a chain. Hold on tight and shout your name. Right, and promenade.
The thing to remember here is that when a carbon atom grabs hold of another atom,
Grab your partner.
like that, you do it with real force, like a really tight handshake. So there's energy in the bond.
That's right. That's the nature of the grip or the bond. It's stored right now. It's stored in that firm handshake.
So what holds the atoms together then, and what holds creatures together, in the end, is energy. But now, here's the surprise. When a creature dies, the atoms inside still hold on, says MIT professor Donald Sadoway.
The idea is that those bonds are strong and they remain strong. They don't require...
Even in death.
Yes.
So, a long, long time ago, there was a sea. It was a shallow sea in what we now call the Middle East. And in that sea, there were little creatures called zooplankton, kind of like jellyfish, and they would swim around all day long, filled with carbon atoms gripped inside, and then they died. And their corpses, upon corpses, millions of years' worth, sank to the bottom of the sea and got squeezed into a mush.
But didn't get so mush that it gave up its hand-holding with other carbon atoms. Well, that's why it's called fossil fuels. Fossils, sort of, the fossil of decaying corpses of plants and living things got pressed into oil.
So the oil then is ancient life, but it's liquefied.
That's right.
But if the energy is still in there, now the question is, how do you get the energy out? Well, if you can make a bond, you can break a bond. We do this all the time, you just don't realize it. Set a log on fire, the fire excites the carbon atoms inside the log, and they break their connections.
So you're really just freeing that carbon from all of its bonds, its hand-holding.
It's the releasing the grip.
And as the atoms unclasp and switch around, they release energy in the form of heat, which is why you get warm when you sit by a fire. Or, here's another form of bond breaking. Eat a carrot. Carrots have carbon locked inside, but when the carrot gets into your stomach, your digestive juices break down the bonds and release calories.
Calorie is a measure of energy.
And that helps you get around. That powers you.
Same thing happens when you put a spark to gasoline. That excites the carbon atoms, breaks the bonds, releases energy, and off you go. So we break carbon bonds all the time, and every time we do, the waste product is the same. Whether it's a fire, a carrot, or an engine, when you break carbon, you get carbon dioxide.
And guess what? When you burn coal, you get the same thing.
And this isn't an accident. Carbon, deep down, yes, is a very social atom. It doesn't like ever being alone. The instant its bonds are broken, it immediately seeks a new mate.
Immediately, that's right.
And whenever it can, whenever possible, what carbon really wants, what makes it most stable, most settled, is to bond permanently with oxygen.
Oxygen is a very happy mate for carbon.
And not just one oxygen, it likes two. Carbon is a polygamist. One carbon plus two oxygens, CO2. That's the perfect union.
That relationship of carbon's lifestyle with oxygen is so happy that it is incredibly stable.
So once carbon finds two oxygens, it clings to them fiercely. Once CO2 is formed, it's very, very hard to pry apart.
Made in heaven. Yep, that's for a long time.
So the more we break those carbon bonds, the more we form CO2 bonds. It's all about the bonds, says Professor Sadoway.
Absolutely. It's all about bonds. It's about making bonds and breaking bonds. It's all about the bond.
James Bond.
No, not that bond, but bonds do matter. One could argue that civilization began when man learned to tame fire, learned how to break carbon bonds. And those fires then became furnaces, and then factories and engines breaking more carbon bonds. Then people got cars and planes and appliances breaking more carbon bonds. And as people on Earth get richer, they use more and more and more carbon, and when they break bonds, we get more and more and more carbon dioxide.
The richer you are, the more carbon dioxide you're making because you're using more carbon, because you're using more energy.
And carbon that's been hiding for eons deep in the Earth gets pulled to the surface.
Now we've freed it, and it's out there, and it's in our oceans, it's in our sky, and it's in our ground.
And because CO2 doesn't dissolve or go away, the oceans can absorb some, trees can absorb some, but we're making more than our trees and oceans can handle, so we end up with more and more CO2 in the air.
That's scientific fact. We know scientists have been monitoring this for years, and the world is filling up with carbon dioxide.
And the problem is when sunshine hits the Earth and then bounces back up to the sky, it now bumps into all those new carbon dioxide molecules floating up there in the air, which warms those molecules, which then warms the air, which warms the oceans, which melts the glaciers, which raises the seas, and that's when you get a greenhouse effect. Classic global warming. Not to mention global warming movies.
We could see a wind-driven storm surge that could threaten the entire eastern
But
seaboard.
even if you think,
This is unbelievable.
which it is, still, says Professor Nocera,
We should be worrying about this carbon dioxide.
because we can't afford to get too much warmer. So what are our options? Well, we can't stop people from using carbon. We can't stop people from wanting to get richer. And most of all, we can't stop a carbon atom from behaving like a carbon atom.
Because that's what the laws of nature say, and it does what it's supposed to do.
But while carbon's nature is fixed, people happily can be flexible. There may be ways, new ways, to use less carbon or capture carbon dioxide, but they will not be cheap.
It's going to be really tough. Scientifically and engineering wise, I think we can do it, but it's going to be the will of the people how much they want to do it.
Because in the end, global warming is less about science than it is about choice. Carbon can't choose. People can. Robert Krulwich, NPR News, New York.